Hello everyone, this is James. I'm a computer science graduate and teacher. Today we're going to look into A-Level Computer Science Chapter 21, Security. This is the chapter outline. We'll look into what encryption is and how it ensures that data transmitted online is safe. So let's look into encryption. It's essential when transmitting data over a network. So for example, when you're transmitting data like this, a message to your friend, you don't want other people to read your data. That's when encryption comes in to make it meaningless. And then from here, you are protected from unauthorized access or interception by converting it into a secure and unreadable format. So something like that. And here's a few terminologies you need to know. Before a text is encrypted, we call it plain text, plain. And when they are encrypted, the term that we use, the one thing that we use to encrypt the data is we use the key. And once the data is encrypted, we call it ciphertext. And you can decrypt the data going through this process to make the ciphertext to once again be recovered to plain text. So for example, hello, I am A is a plain text. Once you encrypted it, it becomes a ciphertext. And once you decrypted it again, it returns to its original message. So that's some terminology. And here are a few security concerns when transmitting data online: confidentiality, authenticity, integrity, non-repudiation, availability. So the description of it is as such. You can read it from the slide. And what encryption solves is mainly the top three security concerns: confidentiality, authenticity, integrity. And we'll talk about how encryption ensures that these concerns are being taken care of. Now, let's start off with a few encryption methods that are available. We won't go into details of it until later part of the video, just to give you an overview. First, symmetric key encryption. I also call it the simple one. It uses a single key for both encryption and decryption of data. So this is the key, and they are used in encryption and decryption. And the key are the same in both the sender side and also the receiver side. And the main disadvantage of using this approach is that whoever that has the key will be able to decrypt the message. And this makes it very unsafe, because what if someone intercept the key that you send to the receiver? So that's just one disadvantage, because we share the key. As a result, computer scientists come up with asymmetric encryption. It uses two keys. First, we have the public key, which is only used for encryption, and also private key that is only used for decryption. We'll look into how this method is a lot safer in the later part of the video. So how does asymmetric encryption work? Where do we get the public and the private key? Imagine that this is the protagonist of this lecture, and he wants other people to send message to him. And this is when this guy will share his public key to every single one, everybody on the network that will need to send him a message. And the public key will be used to encrypt the message. For example, I'm using back the same plain text and ciphertext. Public key can be used to encrypt a message. And when it comes to decrypting the message, the person will then use his private key to decrypt a message from the ciphertext to the plain text. And the advantage of this is that because the private key is always with this guy, that means that there's less risk of other people being able to decrypt the message. Because even though other people have the key to encrypt the message, all they can do is encryption, but not decryption. But of course, sometimes everybody needs to be able to send and receive from other people. This is why, to allow intercommunication among the 5 individuals, they need to have their own private key, and they also need to send their public key to everybody. So if you look at this person here, he has 4 public key, the pink color key, and each of this key allowed him to send message to each of the person and the network. Now we've looked into the fundamentals of encryption, And now we're going to look into the application of encryption, which is first and foremost to create a digital signature. Well, what is a digital signature? It's a cryptographic technique used to verify the authenticity and integrity of digital data, crucial for ensuring the validity and non-repudiation of electronic documents or transactions. Which means, in other words, we want to make sure that when we receive a message, this message is indeed being sent by the sender and not someone else, just so that there is no other people pretending to be someone else. So let's look into how we can verify the identity of the sender. So imagine this is the encryption and decryption process. So first we can ask the sender to encrypt a message using a private key, and then we can decrypt it using the public key. So this method will allow us to, it's like a reverse process, yeah? And then it allows us to know this message is indeed from the sender. But the disadvantage is that sometimes for the whole message to be encrypted, this could lead to slower result. How can we make it the process faster? Instead of encrypting the whole message, we encrypt only the digest. And a digest is a number created using a public cryptographic one-way hash function. So I showed a diagram to explain how this works. Oops. And then, look, imagine we have the plain text. Instead of encrypting this, we put it into a hash function so that it gives us the digest, which is a number. And then we'll encrypt the digest instead, and that will become the digital signature. I know this can be confusing, but just stay with me for a little while longer. And I've created this image to further illustrate what a digest is. Imagine this is a message. You can put it into the hash function. This is the inbuilt function in Python, and it'll create a digest. And this is how the digest will look like. And if, as you can see, the digest here is a lot shorter than the message. And for every single unique message, you get different digests. So that, of course, requires a good hash function, but that's out of the scope of this lecture. So now, with the encrypted digest, we can send it alongside with the plain text, which is not encrypted, and then send it to the receiver. Again, just to remind you, our goal is that the receiver should be able to verify that the sender is indeed the one that is shown on his or her devices. Now, when the message arrives at the receiving end, how does the receiver verify the identity of the sender? This is the process. First of all, the receiver will again put the plain text into the hash function to get the digest. Okay? And then the receiver will also take the encrypted digest. He will decrypt it using the sender's public key. And then now you should have the original digest that the sender has created in the sender side. And the third step is to compare the two digests to check whether the message is authentic and has been transmitted unaltered. So with this approach, you're not just able to verify the identity of the sender, you can also speed up the process. So that's the essence of digital signature. But we still have one problem. The authenticity only confirms to the receiver that the message was sent from the person who had sent them the public key. Alright? But the problem is it does not consider the fact that someone might create a public key and pretend to be someone else. And if this happened, you might have sent some random people data that you don't want. This is why a third party is coming in. We call it certification authority. So a certificate authority, CA, is a trusted entity responsible for issuing digital certificate that verify the authenticity of identities of entities in electronic communications or transactions. So now, with this third-party authority, person A can no longer just send a public key directly to person B. They have to go through this third party that verifies the identity of person A. So how does it work? Person A contacts a CA, and then they said you are indeed A, confirms the identity of person A. Maybe they'll get some the identification number or government document. And person A will then send the public key to the certification authority. Look, he's no longer sending it to the receiver. We send it to the third party. And the CA generates a public key certificate containing person's A public key. And it employs encryption using its private key to append a digital signature to this site. Now, the digital certificate is then given to person A, and then person A will post the digital certificate on the website. Now, what happened when we want to send this person's data? Anyone who wishes to extract the public key from the certificate has to use the CA's public key. Remember, the digital signature is created using the CA private key. Alright, so that's the process. In essence, we take in a third-party authority to ensure that the public key is indeed sent by whoever that wants us to send them data. Alright, so now we have looked into how encryption works and how its application in creating a digital signature, we'll look into specifically how the different encryption methods work. We know that we have symmetric and asymmetric encryption. Now let's look into the process of making of encryption. Now imagine that this is a data that we want to encrypt, and there are two stages of symmetric encryption. We'll first create the key, two 8-bit keys from a 10-bit key, and in stage 2, we'll encrypt the data using the two 8-bits key generated. Now let me show you what it means. Assuming that this is the 10-bit key that we select, so there are 10 bits here, the first step involves permutating the key. So what it means here is that if you look into the before and after process, it says that in this process, the second bit of the key will be here. And then basically, the first bit will be put into the second position, and the second bit will put into the 7th position, 1, 2, 3, 4, 5, 6, 7, 1. And the third bit will be put into the 9th position, and the fourth bit will be put into the first position. So basically, we are just rearranging the key randomly. And after the permutation process, we should have gotten the same 10-bit key, but in a different order. So now we'll apply the circular shift to the left and right 5-bit. So this is the first 5-bit represented by pink color, and the last 5 bits represented by the blue color. Alright, and then circular shift means we move 1 bit to the left each side, and then this one, because it is the leftmost bit, we'll move it towards the end, the rightmost side of this. So this is what we meant by circular shifting. And then after the circular shifting, we'll create the first 8-bit key again using permutation, and basically just take position 3, position 7, and then position 10. So now that's how we shorten the key. And then using another permutation, we'll get our second 8-bit key. So these are the key generated from the 10-bit key. I want you to see that the process is really not so simple, even though it's called simplified. That will make it hard to decrypt the message in this encryption method. Now, once the keys are generated, that's stage 1. Here we have the encryption process. So just a recap, this is our data, and this is the key that we have generated. So again, the encryption process also involves permutation. So what happened here is that I'm taking the second bit, I put it here, first bit, I put it here, and 8-bit, I put it here. So again, reshuffle the data, and then we'll apply a function using the permuted code. And this is a permuted code and key number 1. And the function could be an XOR operation. Remember, an XOR operation will give you an output of 1 when either one of the inputs is 1. So 1, 0, I got 1. 0, 1, I got 1. 0, 1, I got 1. 1, 0, blah, blah, blah. Basically all 1 because all of them are either 1. So then the next step is to switch the last and first 4 parts. So in this case, it doesn't make a difference because they are the same. And then apply a function using the resultant code and key number 2. Again, the function could also be an XOR operation, and then the resultant code. So a final permutation using the reverse of the initial permutation sequence, which is what we just shown you just now. And then the final code. I won't go through the permutation again. Then the decryption by the receiver of the transmission, they can just use the same 8-bit key and follow the reverse of the above process. And this will allow the receiver to decrypt the message. So this is how simplified data encryption works. As you can see from this process, both the sender and the receiver, they are using the same key. So that's just one aspect of why we say symmetric encryption can be quite unsafe. And in the advanced encryption standard, previously we are doing the simplified one, but in the advanced standard, they uses block length of 128 bits, which is a lot bigger than what we just do. And the requirement of securely sharing and managing the key between both the sender and receiver in AES raises concern about key distribution, storage, and potential vulnerability if the keys are compromised during transmission or storage. Basically, it says that it's quite dangerous to transmit the key or to even store the key because someone will just snatch it. And this makes sense because once anyone have the key, they can reverse the whole process and get the message that you send to people. Now, that's symmetric encryption. Now let's look into public key encryption method. And one of them is called the reverse Shamil and Edelman method. So basically these 3 people are the founder of this algorithm. So let's look into how public key can be generated. Now, first of all, 2 very large prime number. Prime number means a number that can only be divided by itself and also 1. They are chosen and their product is calculated using n equal to p times q. I'm highlighting the important term here, so just take note. And the product p minus 1 times q minus 1 is calculated. And a number smaller than the product that is not a factor of it, so the product smaller than it, e, is chosen. And 65537 is usually the choice. And then we'll find another term called d. How do we do that? We basically use this formula, p minus 1 times q minus 1 divided by d, which is what we just calculated, and e must give a remainder of 1. So this is like a linear equation. You have to find d here. As long as this equation gives a remainder of 1, then that's your d. And then the public key will be n, comma e, and then private key will be n, comma d. Of course, in this case, there's a side note here. It is not so easy to deduce p and q. Hopefully now you can see that it's a very mathematical thing. Nothing really magical about it. So public key encryption, although it is more secure, because only public key cannot be used to decrypt a message, it tends to have slower algorithm. It is a common practice to employ public key encryption for securely transmitting a key that can subsequently be used for faster symmetric key encryption. So basically, even though symmetric encryption is not so safe, but symmetric and asymmetric encryption are often used together to make sure that it is not just safe, but also fast. Alright, so now let's look into some upper layer of security, which is what is used in the web pages. Okay, SSL, Secure Socket Layer. It is essential for ensuring the authenticity of a website to make sure that you don't go into a fake website created by other people. And facilitating secure transmission of sensitive data by encrypting. And this data could be your credit card details, your password. So basically, this SSL applies everything that we just learned in the previous chapter. So I put a recap here. Now, SSL operates at the application layer. We talk about it in the network chapter of the OSI model, and is commonly implemented on top of the transport layer protocol, typically TCP. It uses port number 443, so this is just some information for secure communication. SSL provides a secure channel between a client and a server, ensuring confidentiality and integrity of data exchange during communication. So there are a bunch of words here, so I figured it would be better to show you image form. So when SSL in place, you'll get HTTPS. That's the first thing you need to remember. And then SSL is also a protocol that involves these little protocol suite that involve this protocol. The record protocol is used to encrypt, authenticate, and fragments data. And the handshake protocol facilitate the negotiation of security parameter and mutual authentication to establish a secure connection between a client and server. So let me explain what has just been mentioned here in image. And there are a few steps in SSL operation. First, the SSL operation starts when the client wants to establish a connection with the server, which is in this image here. And then the client browser will then invoke the handshake protocol from the SSP suite. The handshake protocol will request from the server its SSL certificate that can confirm its identity. So remember the certificate that we just created, that is issued by the certification authority. And then the server sends its SSL certificate plus its public key to the client, and the browser employed the public key to encrypt a key, serving as a temporary session key for symmetric key encryption during the data transfer in that session. So this is the process of it. Basically, without a certificate, we want to try avoiding sending our data to them, because we might not know whether the website that we are visiting are genuine or not. Of course, this is SSL, but most of the application today, they uses TLS. It's an upgraded version of SSL, because SSL, apparently there are some security issues attached to it. All right, compared to SSL, TSL has stronger cryptographic algorithms and improved protocol. Now let's look into the last subtopic for this chapter, which involves a little bit of physics, quantum mechanics. So this field of physics explores the behavior of particles on the smaller scales, challenging classical understanding with phenomena like wave-like duality. So this is photon, particles that transmit light, and this field of cryptography uses photon. So let me explain. So photon exhibit wave-like characteristic, causing each photon to oscillate in specific direction. So they can oscillate in terms of horizontal and vertical, but also sometimes diagonally. And this directional oscillation, termed polarization, is illustrated here. And how this works, the algorithm that uses photon is called quantum key distribution, a secure communication method that leverages quantum mechanical properties to exchange cryptographic keys between parties. Now, let's see how it works, because I think from the definition, it's really hard to understand it. So the sender will choose bit pattern at random, basically just send a random string of bit, and then the user will also decide how the light photon should oscillate. So the plus signifies the horizontal and vertical, and X stands for diagonally. And then the receiver will also select the polarization basis randomly. The key here is that, okay, let's read this. Following the transfer, the sender informs the receiver about the polarization basis used for each value. The receiver responds by saying which one were chosen to match. So only when the polarizations are equal to each other that the bit will be considered. So for example, in this case, this one bit here will be ignored because the polarization are not the same. So when we only take in the bits in which the polarization are the same, that's why the secret code is 00110. And for each bit, only when the polarization basis, that's what I just said. And by using this method, of Of course, there are more to it. I'll attach a video in the video description. I think that guy explained better than I can in this topic. But that's the essence of quantum key distribution. They use this characteristic of photon to be like a key. And one thing that is good about photon is that if anyone tried to intercept it, then the bit will not be transmitted because it's photon. It's not bit. It will be, once it's intercepted, it will just be gone, and the receiver will know that someone is doing something bad behind the hood. So the advantage of QKD, the exchange doesn't include specific values, only photon. According to the principle of quantum mechanics, any attempt to intercept and determine the polarization of these photons will unavoidably disrupt or destroy them. A photon cannot be detected, measured, and then forwarded again. So that's what I just said. If you try to intercept it, and you need to know what polarization the sender and receiver are using. And that's a little bit difficult. That makes it hard to decode it. And the disadvantage of QKD is incompatibility with standard communication media, necessitating the use of dedicated quantum channels for secure key exchange. So this makes routine use unlikely, but of course research is now being conducted to make this a reality. But for now, this is just a really good concept, but not so practical. So that's the end of this chapter, security. Let me know in the comment section if you have any questions. I'll be happy to help. Thank you so much for watching. I'll see you in the next video. Goodbye.